Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Hopefully you guys are doing well. Let's jump into it. So last time, we didn't really do much by way of actual material, but we went over the syllabus, so we kind of knew what the plan is. Hopefully you tried to sign up for the homework already and actually read through this. Today we're going to be covering section 2.5 and 2.6, which is exponential and log functions, as well as I asked you guys if everyone received email communications from all the places I tried to send it, and I did get some responses, and I haven't responded to everyone. I did to some people, but yesterday I also started getting a lot of new students registering for my class. So I figured I'd wait a couple days and just update everyone at the same time. So just to make sure that I don't get confused and miss anyone. So I'll update the people who are already on my roster, but for some reason didn't get any communications, as well as students who are brand new to my roster, but didn't get any communication. So I don't think there was anyone new in this class, but hopefully. So I would say by the end of the week, if you don't hear from me through the means that you said you could not hear from me, then shoot me an email. But for now, just relax. You can assume that I got the email that you sent, but I'm just not responding to it. I'm waiting for a little bit. Okay. Now let's actually get to the matter at hand. And I'm not sure if, so I'm going to be writing everything here. I'm not sure if I want to, should I do the lines so I don't look like I'm writing all over the place? That's so weird. Normally I pre-type the notes, but I wanted to pace myself a little bit more this semester. So I want to write everything out for you guys, but then I don't want to like write on an angle and it looks weird. This is very weird to me. Okay. So maybe we'll do that. Was this the class that I had audio issues with yesterday? Okay, so it wasn't you guys. All right, never mind then. Can someone actually say something audibly so I know that I'm connected and I can hear?
Good morning.
Awesome. Okay, I heard that. Good. Let's jump into it. So not going to do anything too crazy today, just pretty introductory. A lot of you would probably know most or everything about what I'm going to say today, but I just want to make sure that we're all on the same page. And I'll also point out some things that perhaps have not been pointed out to you before, but for the most part, it's not going to be anything too crazy. We're starting with exponentials and logarithms. The implicit assumption is that you guys already know about polynomials. So things like what a straight line function looks like, what a quadratic would look like, cubics, quartics, etc. And to some extent rational functions, but not that much. We're not going to use that very much here. But that's the implicit assumption. So we're starting out at exponentials and logarithms because students tend to know a little bit less about those things. So it might seem very familiar, but let's make sure that we are all on the same page. So let's start out with I don't know what happened there. Let's start out with exponentials. So what I want to look at first is the laws of exponentials. Exponentials, you might know these as powers, aka powers. So those are the little numbers that you write to the top right corner of something, okay? And there are some rules that you should know about these guys. So one is that if I have something raised to an exponential and multiply by something else raised to another exponential, what is the result? Does anyone remember?
Don't you add
A
them?
plus B.
You add them, right? So it's x to the a plus b. What if we're dividing them?
Subtract.
You subtract the exponents. And what if we are, computers are giving trouble today. What if we take something to an exponent and we raise it to another exponent?
Multiply.
The exponents.
That's when you multiply the exponents. What if we raise something to a 0 power?
1.
It becomes 1. Assuming the thing itself is not 0, right? 0 to the 0 is not really defined. And the reason why we know that is because you can think of x to the 0 as something like x to the 1 divided by x to the 1, which gives you x to the 1 minus 1, which is x to the 0. And you know that this has to be 1, so that makes it 1. However, division by 0 is not a thing, so x cannot be 0. 5. What other rules do I want to make sure you know? X to the 1 is just x. I mean, I think everyone would be on board with that. The sixth thing, if I'm multiplying two things and I raise them to an exponent, the exponents actually distribute. Exponents distribute across products. Warning. Not true for sums. In the sense that if I had x plus y raised to a power, it's not the same as just saying x to that power plus y to that power in general. It's true if your a is 1, but it's not true in general. So exponents can distribute across products. They can also distribute across divisions because a division is very similar to a product. You can think of dividing by something as multiplying by its reciprocal. So if it distributes across products, it will distribute across divisions as well. What does a negative power mean?
Inverse.
Inverse as in reciprocal, I think you mean.
Yes.
Again, x is not equal to 0 in this case. I do want you to note negative exponent does not affect the sign of the base. Right? So when we are talking about exponents, we're talking about things that look like some big thing here and some small thing there, where the big thing at the bottom, that's called the base. And the thing at the top, that's called the exponent or power. Occasionally, I see students get confused. They think they have to put a negative sign down here or something like that. This is not true. The sign in the exponent does not affect the sign of the base. A negative in the exponent just means to take the reciprocal. What else? Here's a fun one. What if I had a fraction in the power? You guys remember that?
Radical and
who goes on the radical?
B.
The b goes on the radical and the a goes up here. And occasionally you can switch them. You can put the radical and then take the power. as long as your x is greater than or equal to 0. Okay. So that's something that sometimes I refer to in my classes as flower power, because you just to make sure that you remember this, there's something called flower power. And it kind of comes from the idea where if you have something to a fractional power, you imagine that that thing here is like a flower. And the bottom part of the flower is the root, or the thing that goes on the radical. The top part of the flower is, of course, the flower, which rhymes with power. So we know that the top number, which is the A, should be in the power, and the bottom number, which is the B, which is under the ground, should be the root. Root, like square root, is another name for radical. Okay, so, all right, good. Okay, so those are just some basic rules that we need to remember, and it seems like most of you do. Awesome. Let's actually talk about exponential functions. So here's the basic function. So these are functions of the form y equals a to the x, where a is a constant, so it's just a number, and x is the independent variable. Okay. Usually, we take a to be greater than 0. And that's because when you have a negative in the base, you can get issues. For example, if your power becomes a fraction like 1/2, 1/2 is equivalent to taking the square root, and the square root of a negative number gets weird. So if you're not in a class where you're allowed to use complex analysis and things like that, and you're not talking about imaginary numbers and complex numbers, which in this class we're not, then when the base goes negative, things get weird. So we'll tend to think of the base as positive. In fact, most of the time, we'll tend to want to write the base in such a way that it's larger than 1. And we can always get that to happen, because if the base is less than 1, we'll be able to use rule 8 and write it as something that's larger than 1. So let's say I had a base of 1/2, right? So if I have 1/2 to the x, what I could do is I can just make the x negative, and now the base can flip, and I can write it as 2 to the negative x, right? So once something is positive, I'll always be able to maneuver it in such a way as to write it so that the base is larger than 1. So oftentimes we're going to actually think of the base as being larger than 1. Base, no pun intended, base rules on a larger than 1. Okay, all right, so that's just, so examples. So if I have y equals 2 to the x, that is an exponential. Or y equals 1/2 to the x, that is an exponential function. Notice that this guy, by the way, is the same as saying 2 to the minus x, right? So in the first situation, we wrote the base, it's positive, it's 1/2, but it's less than 1. But I could rewrite it in a way such that the base is larger than 1. So you should just be aware that we can always actually do that. However, so y equals x squared, not an exponential. In fact, this is what we call a polynomial function. Here, y equals something like 3 times 5 to the x plus 7. These are all examples. This is a non-example, right? So you should be aware that we can generalize using transformations, so on and so forth. But at this point, you don't really need to know what that is. I just want you to have the idea that if I take something that's of this basic form, a to the x, I'm allowed to multiply it by a constant and it's still considered an exponential function. I'm also allowed to add a number separately and it's still considered an exponential function. So something like y equals b times a to the x plus c is also considered exponential. Okay. So hopefully you're all with me so far. And I know I'm not saying anything new to a lot of you, but just to be safe, it's just day 2. Let's start out slow. Let's not do anything crazy. Note, exponential functions obey the laws of exponents. Right, which is why I had to tell you them about those guys in the first place. I.e., if I have something that looks like 2 to the x, and that's one function, so I can say, f of x equals 2 to the x, and g of x equals, say, make that another variable. Let's say these are tracking 2 different things, g to the y equals 2 to the y. Then the function f times g would look like 2 to the x times 2 to the y equals 2 to the x plus y. Right? So you can actually create a new function that encompasses both functions at the same time, and you can combine exponential functions using the laws of exponents, but they'll still be exponential functions. What I want to talk about now are the graphs of exponential functions. Okay. So now assume a is larger than 1. And now you know that it's fine for us to assume this, because even if a is not larger than 1, I can write it in such a way that a is larger than 1, right? So if my base is smaller than 1, but it's positive, I can just make a negative exponent to write it as something that's larger than 1. So if we can understand the case of being larger than 1, we essentially can understand all cases. So the graph of y equals a to the x, I don't know if do I want to. The graph of that looks like, and it passes through the point 1 because of the laws of exponents. When my x is equal to 0, my output is going to be 1. Right, so that's the graph of that exponential. If I were to do something like write as a to the minus x, then the graph is going to look like this. Should probably make it look a little bit more like the last one. And this again passes through 1. So that's what those two graphs look like. If I were to do something like something wrong here. If I were to do something like put a negative on the base, you should know that that flips a graph upside down. It reflects it in the horizontal axis. So we'll actually go like that. So we'll pass through -1. And if I were to do something like y equals -a to the minus x, that is going to flip this one upside down. So it's going to look like that. This will be -1. Obviously not drawn to scale. So those are the basic graphs of exponential functions. And you guys should remember things like, well, if I were to add a number to this, like a to the x plus a number, if that number is positive, it will just take this picture and it will shift it up. If the number is negative, it shifts it down. And if I multiply it by a number and that number is larger than 1, it'll stretch it vertically. So it'll actually appear to rise even faster. And if that number is less than 1, it will squish it. Okay. So, but those are the basic graphs. Now, here is something that is important. It's something that a lot of everyone who like covers these things in math or calculus or engineering, they're aware of this. But after telling you about this fact, I'm just kind of going to illustrate why it would be important for a business major or just any general human being to actually know this fact. Important fact. Exponentials grow faster than polynomials. Okay, in the sense that, i.e., an increasing exponential will eventually surpass any polynomial. This idea is expressed something like the following. If I have a to the x, someone's coming in. That is going to be seen as, we use this expression here, as much larger than something like x to the a. As x goes off to infinity and say a is larger than 1. Okay, so this is something that again, as a mathematical concept, a lot of people know it. Oh, exponentials grow faster than polynomials. Note. Let's compare two things. Compare. Let's say I wanted to compare y equals x squared to y equals 2 to the x. Okay. Let's say I'm going to sketch this one in red, and I'm going to sketch this one in blue. Okay. So tell me, what does y equals x squared look like?
Just a u.
It's like a u, right? And it passes through the origin. Okay, good. Okay, not so bad. Okay, all right. And just the 2 to the x. Well, I kind of told you what that would look like already. It would look like this. Passing through 1. Right? Now that is what we call expectation, right? And not a math, like I'm kind of using this like a meme, right? Versus reality, expectation versus reality, right? Because this is going to be very important for you to understand, right? Does not seem much different. That sentence sounds weird to me. Whatever, I'm not an English teacher. Okay, right? So a lot of times students draw things on this scale and are like, okay, I see the y equals x squared, and I see the 2 to the x, and I know that one is shaped like a u and one is done like that. And a lot of students just kind of run with that, right? But here's the thing that you really need to understand. They are not the same, right? We are not the same, okay? So here's how I want to kind of illustrate that to you. Let's say now we're looking way out, like we're going off to infinity. X is getting huge, a bajillion, gajillion, quadrillion, capillion, quadrillion, right? Like a huge number, right? So what does my 2 to the x look like? It looks like this. Okay. Now remember, this is huge, okay? Can anyone tell me what the x squared would look like? It's like a u?
Yeah, but
The
wouldn't
u
it be
be
wider?
pushed horizontally.
Yeah, okay. Now that is very natural to think that way, but it's not true. On a large scale, when I say something like this, right, I want you to understand what that means. On a large scale, I think I did the x squared in blue. Here's what x squared would look like. Effectively 0. Eventually, an exponential will grow so fast that any other polynomial, once you zoom out, might as well not even try. It's not even there. I can't even see it. It's nothing. It's 0. The exponential will rise so fast that anything rising at the speed of a polynomial will eventually vanish in the distance. Not even close. Not the same thing. On a small scale, they might look similar. So on a small scale, they look similar. But on a large, they're not the same, okay? And now why is that important? So here's the thing. For whatever reason, human beings, we're very good, even those of us who aren't good at math, we're very good at conceptualizing something that grows like a polynomial. In particular, something that grows linearly, right? If something is growing like a straight line, we have a good concept of what that means. You know, like it's very intuitive to us, right? So if you were to guess, okay, this thing is growing like a straight line. And if I were to tell you, oh, tomorrow, how much do you expect there to be? Most people kind of guess, most people actually be on point with their guessing. Whenever something is growing exponentially, human beings are not good at guessing. They're not good at noticing. So it's like they can sit and they can watch something growing exponentially, and they're probably not going to notice much difference between that and something that's growing like a straight line. Just like on these two graphs, yeah, I mean, the shape is different, but when I'm going off to the right, the blue curve and the red curve, they're kind of doing the same thing. I don't really notice a difference here. However, if a person watching something growing exponentially were to walk away for 10 years, 20 years, 30 years, and they were to come back and check where they expected things to be, holy cow, when did this happen, right? So it's going to like surprise them. So even people like Einstein said, you know, compound interest is one of the wonders of the world, right? Because things that grow compoundingly it grows in such a way that human beings are just amazed by it. You know, like how cats are amazed by lasers, like human beings are like that amazed by it. And there are all these phenomenons that happen in the world that a lot of people don't appreciate because they're actually more exponential than they are linear. So, for example, you ever notice how the ultra rich people seem to just get ultra richer? Right? Even if they're into all this philanthropy and they're giving away millions and billions of their fortune, somehow the following year, they're even richer than they were last year. What's going on? Their money grows exponentially. That's what's going on. So your concept of, dude, if I splurge a little bit 1 week, like my rent is in danger the next week. Whereas this guy gives away $1 billion and now he's still like in the top 5 richest people in the world. What's going on? Your money's linear. His money's exponential. That's what's going on. And here's the thing. If that person still had their money growing exponentially, but they started out with a bank account at your size, you would both kind of be very similar. If he splurged all his money in 1 month, both of you will be in the same boat. However, eventually, because his fortune starts at a higher level and it's growing exponentially, it increases in mind-bogglingly fast, to the point where it's like they can do things that you can't do, right? And it's like it's not the same. Occasionally, there are also these ideas. There's also the notion of some people who did make it really rich and then they lost it all on parties and women and drugs and whatever. And you're like, well, this guy had hundreds of millions of dollars. How did he go to nothing? Versus this other guy who had hundreds of millions of dollars, gave away millions of dollars, and yet he has more the next year. Well, the difference is how these two people invested their money. One person would invest their money into things that grow exponentially, whereas the other person were probably just putting their money in a regular bank account, hiding it under their mattress. Their money is growing linearly, right? So basically, the math says, saving your money under your mattress is a bad idea, essentially, right? So if you're a good saver and you take $100 and you save it every month under your mattress, yeah, your money is going to go like this. You'll have more and more and more and more, but guess what? It'll grow like a straight line. If you were to take that same $100 and put it into some investment that grows exponentially, meaning it doesn't grow by a fixed amount every time. So if you're putting in $100 every month, it means that your fortune is growing by a fixed amount. It's growing by $100 every month. If you were to put it into something that's growing by, say, 10% every month, that's a whole other ballgame, right? So if I put $100 and it grows by 10%, then yeah, the next time I'd have $110. I'd increase by $10. However, the following year, it actually would increase by $11, right? The following year, it's going to actually increase by more. Even if you never put any more money in it, how much it increases by starts to increase, right? And that's this is kind of something that's exhibited in exponential growth. There are other functions that grow like that, but an exponential is essentially something that grows as a fixed percentage, something that always grows at like X% per year, okay? And that makes all the difference. So if you have money that you're saving and you are saving it in a checking account, one, it's a bad idea. Yes, your money will grow, but because of inflation, it's actually going to have less value over time. So it's a bad idea all around. If you were to put your money in an investment that grows, say, 4% per year, that's much better. And in the first few years, after 1 year, 2 year, 5 years, you're not going to notice much difference. You and the guy saving his money in a checking account, you're going to be roughly the same. 30 years down the line, when you're both retiring, that's when you're going to see the difference. One of you is going to be a millionaire, the other one will not be. And it's that much of a difference. And that's the thing. This is not understanding things like this. This is why a lot of people think that math doesn't actually help. I did math in school and I never use it in my life. Yeah, you don't realize when it's happening to you. That's what's going on, right? The understanding the mathematics is what's going to tell you what is the good decision to make if I want to have a certain thing. No one's saving money to just survive, right? You want to thrive, right? The math says if you want to do that, you need to make sure your money is growing exponentially. How you do that is investing, right? You don't just save a fixed amount of money all the time. You need to make sure that whatever you're saving is growing by a percentage amount by itself, right? And that will make all the difference in the world. And this is going to come up with things like compound interest and how amazing it is and why Einstein would make a statement like, oh, compound interest is one of the wonders of the world. Because it's one of those things where in the short term, we don't notice. In the long term, amazing things can happen and mind-boggling things can happen. And the math says so, right? So when a lot of times some students will understand this concept. Yeah, exponentials grow faster than polynomials, but they don't really get the concept. So it's like when I asked you guys what this would do, so you guys still thought, yeah, it would be pretty much U-shaped. Nah, bruh. On a large scale, the polynomial might as well not even try. And honestly, it doesn't even matter what the power is. You don't even have to think of x squared. X to 1,000,000 is going to look like this. X to 1,000,000,000 is going to look like this. X to 1,000,000,000,000 is going to look like this. It'll put up a fight in the short term, but eventually 2 or 1.1 to the x is going to go faster than x to the billion. And that is a very important concept to understand. And it's not a concept that you're going to notice in the short term. It's a concept that happens to you in the long term. Okay, so that's a very important kind of a real world notion that I want you to take away from this. So yeah, I'm talking about the math and all these rules, but I want you to understand the implications of what I'm saying. So hopefully that kind of gave you some idea. Hopefully that's clear. Are there any questions so far on anything I've been saying? Okay, so I guess at this point, I do want to talk about compound interest, what I've been mentioning. Should I talk about simple interest first? I should probably talk about simple interest. No, let's just talk about compound interest. There's going to come a point where we do financial math, and I'll talk about simple interest there. Okay. So compound interest is a real world example. Real world. It's going to still seem very mathy, but it's a real world example. So if you're saving your money in a checking account, it grows essentially linearly. If you're saving your money in a savings account, it will grow more exponentially. However, most commercial banks, the interest that they pay you is the kind of interest that you're it's just effectively, it's going to be like linear. You're never going to notice. By the time your money starts to grow like this on a 0.01% interest rate that you would get from a typical bank, like you'd be dead. Like you're not going to notice. Okay. So for this thing for you to really start noticing things, you want something to grow at like 3%, 4%. You want it to grow at a percentage that's higher than inflation, which is usually roughly around 2%. And so, 3%, 4%, 5%, very typical. Some things grow at 10%. Like in general, the stock market is going to grow at around 8 to 10%. Most realized gains, though, you'll notice at roughly 4 or 5%. That's because of taxes. But yeah, very few things in the world will actually grow larger than 10% compounded. But let's actually not get ahead of ourselves too much. Suppose we have $100 and we invest into an account that grows at, just putting some nice round numbers, 5% per year. No bank account is going to give you 5% per year. I know it's not a realistic example, but I just want to have some nice round numbers just so that you guys can get the idea. Here's what's going to happen. Okay, so year one. Okay, so we have let's start of year one. So we have $100. Okay, what is year two going to look like? Well, you're going to have $100 plus you're going to have 10% off the $100, right? Do we remember how to write 10% as a decimal? Anyone? Hello?
Just 0.1.
0.1. Right? Remember, percent means per century. Per means divide. Century means 100. Percent means divide by 100, right? Percent equals divide by 100. Right? That's why 50% means 50 divided by 100, which is a half. Something grows at 50%, it grows by half as much, right? So 50% and 0.5 are the same thing. 50% and a half are the same thing. Okay. Okay. So essentially, at the start of the second year, you have 100 plus 0.1 times 100. Okay. Which means you can factor out the 100 and you'd have 1 plus 0.1. Okay. Now that's going to be, by the way, that's going to be like 100 and 10%, not 5%. I realized it. That's going to be like 110. Okay. What's going to happen the following year? Well, now you have the 110. Plus, that's going to grow by 10% off the 110. Right? So what is that going to be?
$121.
121. Okay. So I want you to appreciate that it grew by 10% the first year, and it grew by $10 the first year, but it grew by $11 the second year. And you didn't really touch anything, right? So it's growing by more and more every year. So grew by 10 1 year, and this guy grew by 11. Okay. All right. So now I actually want us to do something actionable, because we could, if I were to ask you, oh, what's going to happen in 50 years? I don't want to have to go through all these calculations. So can we make this look a little bit nicer? So the answer is yes. There is a nicer way to think about this. That way is going to be, okay, let's remember year one, we had $100. Year two, we had 100 plus 0.1 times 100. We could do a little bit of math. We can move the 100 out and we think of it as 0.1. Okay. Now here is what we're going to do. On year three, I'm not going to actually calculate the answer. I'm just going to leave things in parentheses like this. Okay. So year three, now I have this amount. Plus, what I'm going to do is I'm going to grow by 10% of that amount. Right? So at first it's going to get a little bit confusing, but it's going to start to make sense in a little bit. Right? Now what I can do, now you'll notice that these two are the same, and I can factor those out. What I would have left over is going to be 1 plus 0.1. But that 1 plus 0.1 is the same as this guy. These two are the same. So I can actually write this as 100 times 1.1 squared. You will notice that this is actually going to be very similar. It will grow. So if I'm at year n, some big N, it's actually going to look like 1 plus 0.1 to the n minus 1. Okay, so I have a nice formulaic way to think about this. And normally, if we took account at the end of the period, then it will bump up by one more. So the amount after n years would be equal to 100 times 1 plus 0.1 to the n. Okay, if we take it after we gain the interest at the end of the year, which usually that's how we calculate it in finance. Right? We do it at the end of the year. So this leads to the compound interest formula. And we will do a lot more with this when we get into finance. So the idea is the following, and that is A equals P 1 plus R over N to the N times T, where A equals the amount after time T, P is what we call the principal, which is the initial amount. R, this is the interest rate. And we think of it as compounded n times per year. And T is the number of years. Yes, so that's a very important formula. we will see it again in the next section, but I want to introduce it as note. If P, R, N are fixed, then this is an exponential function. Okay, so compare. So say we have P growing by K amount per year. Then after T years, we would have A equals P plus K times T. Now this here is linear, which is a polynomial of degree 1. So essentially, and we're actually over time, so I should wrap this up. Essentially, money in your checking account grows according to this formula, right? Which is kind of like an x to the power 1. Money in something that grows compounded interest grows like this formula, where the idea is, hopefully you saw the comparison, it's 1 plus the percentage amount times the number of years. However, sometimes we divide that percentage amount across the year. So sometimes you can get paid interest during the year, like every 6 months. So you'd have your interest paid twice. So you'll actually divide this by a 2. You divide the 0.1 by a 2, and then that's where the division by n comes, and you have to say I'm doing it twice for every t, and so you get the n times t, and you'll have that. And so something growing by compound interest would grow according to this formula. And in the beginning, you're not going to notice much difference between the a's in this formula and that formula. However, over time, the difference is going to be substantial. We're going to stop right there because I'm already over time. But next time, I'll give you some examples on actually a compound interest, where I'm going to give you like a word problem and we can actually work through it together. And then we're going to talk about logarithms. It turns out that when we need to solve for the t, knowing about exponential functions alone isn't enough. We need another kind of function to actually answer certain types of questions. So we will stop right there. Hopefully that wasn't so bad. And we'll pick up on Friday. So any questions before we go? Okay, all right, I guess we will stop there. So thank you for your attention, and see you in the next one.